I am Vinny Scarlata. I work for Intel Labs. I'm one of the SGX architects, which means also if you have miscellaneous SGX questions that have nothing to do with this presentation, you can feel free to track me down during the conference and I probably have answers to them. The topic I want to talk about today isn't SGX architecture in general. We've presented that at many different places. But rather it's to talk about some of the labs work that we've done on interesting usages that go beyond just the standard, well, I have keys to protect, enclaves protects parts of applications, so it's a good fit. The idea is there are some richer, more interesting usages out there to talk about, and that's what I want to use my time for today. Standard disclaimer stuff. Anybody listening to half of today would know there is no such thing as absolute security. And if you still think that, you are really sleeping today. I'm going to assume most people have at least a high-level understanding of enclaves, but I'll give just enough background to make sure that everybody is on the same page. SGX, Software Guard Extensions, is our application isolation technology. The idea there was, in the past, isolation technologies have had TCBs that were just too large to be tractable. And the gentleman a couple of steps ago was talking about how do you create a trustworthy platform? Well, when you have millions and millions of lines of code, the answer is probably never can. So the idea there was to shrink it down to just your core assets and the code that needs to operate on them, and protect those assets from software attacks on the platform of all privilege levels. Don't assume that the entity that owns the platform is a good guy. It could be, we have many usages, particularly in the cloud, where you're hoping they're not hostile, but you're also hoping not to have to trust the entity that owns the platform. We added increased protection for certain types of hardware attacks. We don't make smart cards, but we were talking earlier about all the different things you can do if you can start poking at buses, the buses that SGX relies on. We've taken steps to add additional protection to those buses. At a minimum, those buses are encrypted. And then most security technologies are only as interesting as your ability to know that you are actually successfully using them. So we have hardware-based attestation that'll let you ensure that the device you're communicating with on the other end is a real Intel device, and find out what software is actually in the enclave so you can make sure that it is what you're expecting. And then the whole idea here is that by putting this inside of our main processor instead of a secondary processor, is that we have the full horsepower of the server that you're running on. So if you're on one of our big Xeon processors, that'll have significantly more power than some small coprocessor thing. But before I dive into the usages, several of our usages benefited significantly from some techniques that we have for making enclaves easier to use. And that is that we designed enclaves to have that super small TCB, but that requires, it might be easy-ish if you're creating your application from scratch, but if you have an existing application, then refactoring can be a very time-consuming, long process. And so as a stepping stone between your application today and eventually having the smallest TCB possible protected, you can use library OS projects that are currently being used for all of your different container projects. In our case, the labs has been working significantly with Graphene. And if you're not familiar with the library OS, it's just very simple. You create a container and you have the libOS that exposes your system calls up to your unmodified process. And then this makes a nice self-contained package that you're able to deploy. Well, that's great for deploying in the cloud, but it's also great for establishing a perimeter for your enclave. So this was inspired by Drawbridge, and then we've sort of taken the same cue Haven did to add SGX to the picture, and we've worked with some universities and open sourced the Graphene SGX version, which takes unmodified applications, can be Docker images, and puts them into an enclave. And this allows us to support things that the the refactoring model does not. You can't really load dynamic libraries in the normal SGX model. You can here. This supports languages like C and Python and R. There are certain pieces that apply to SGX that do not apply directly to containers. That would be things like the sealing mechanisms and the attestation mechanisms. Your application isn't really going to get the full benefit of SGX unless it uses those. But the point was to have an unmodified application. So what we've done is we've extended Graphene and added in transparent shields to your network I/O and your file system I/O system calls to transparently and inline add remotely attested TLS sessions to your network traffic. So the other end is able to see, okay, I am communicating with this particular application that's sitting on top of this particular Graphene OS, all wrapped in an enclave together. And our traffic is protected by the TLS session that I negotiated. And then for file I/O, we put a similar inline encryption. But the trick there is SGX provides hardware seal keys, but you don't want to use those in the cloud because next time you're going to be somewhere else. So we added a couple of hooks to let you provide those keys in a couple of different ways so that it'll use the hardware keys if you want it to, but if you configure Graphene differently, then it'll let you fetch the keys some other way. And so with that, now let's talk about some of the usages that are using that and some of the ones that are not. So here's 8 interesting usages. Because we're running so far behind, the top row of these usages are sort of the obvious things that you could do with SGX. And then the bottom row are the more interesting ones that sort of pave the way for the rest of the presentation I'll do deep dives on them individually. I won't spend as much time on the top ones to try and get back some of our time. Obviously, the first one, as I mentioned, if you've got keys in your application, then very high probability that SGX can help you protect those keys. HSMs are an interesting usage. We can build what we refer to as a logical HSM, which is basically where you take the HSM software and put it in an enclave. We do not believe that, or we are not promoting that this is a replacement for HSMs, but HSMs are very expensive, so many people don't use HSMs. And they have no choice but to leave their keys sitting around in very unprotected places. Whereas we believe that an enclave-protected logical HSM can be a very inexpensive middle ground that is significantly better than sitting on a file system for those that can't get all the way to a hardware HSM. Coming out of the conversation before, obviously a lot of IoT devices are starting to handle more and more sensitive data, and anything that helps to protect that data on those devices is a move in the right direction. So now onto the bottom row. Enhanced privacy analytics, or sometimes referred to as privacy-preserving analytics, is a cool concept that's best illustrated with a concrete example, which would be doing health research to try and do things like mine the genome for patterns between sick people and healthy people. You've got a whole bunch of hospitals and insurance companies, and these guys have lots of patient data, obviously very sensitive. None of them want to trust anybody else with their patient data. And then you have a whole bunch of researchers who really just want to access that data and are perfectly happy living within some privacy constraints. You can run these sorts of queries, but not these sort. You can do these sorts of activities as long as the results are anonymized on the way out. And between the mining, whatever queries they're going to do, they may find to be very sensitive because it's sort of, if you can watch that, it leads you towards what sort of research they're doing and can be interesting to their competitors. So really what you want is a place that you can put all the queries and all the data where everyone involved knows exactly what the logic is that is in that place. And the data providers can tell, yes, this will not satisfy any queries that are outside of this set of policies. And the query owners are able to say, my query won't be exposed to anybody else. And this is sort of the definition of what SGX attestation is for, right? If everybody was to pour this data into a place where it's accessible to the enclave, everybody can get attestation of the enclave and see, this is the open source query engine that I've looked at it and I know that it will handle my data or my queries the way I expect. It'll anonymize the results to protect my patients. All these sorts of things will be handled because I've seen the code and the attestation says that that's what's there. And this, you can spread it past the health industry to finance or all sorts of other interesting places where you have lots of data from distrusting entities that want to sort of sell controlled access to the data, if you will. The next three will go into deeper, so I'll probably just reference them by name. They're just sort of the agenda for the rest, which is we'll talk about how 5G infrastructure can use enclaves to build cheaper infrastructure that is safer than software alone. Blockchain, we believe that leveraging SGX, we can significantly decrease the power cost of blockchain algorithms and be still able to meet the security needs of some usages. And then machine learning, well, obviously, with all of our interesting data off our phones, making it into the cloud and being mined, trying to protect that data is a big topic recently and will continue to be a big topic. So let's get started with machine learning. So there are two interesting scenarios from our perspective for machine learning. Sort of the first one is as a service in a cloud environment. Either the cloud provider has their own models that they've spent significant amounts of money training the models and being ready to offer a facial recognition, object recognition, speech recognition as a service where the customer just provides the data. Or you could have a similar service which is more just the classic cloud model of you've got the computation space, I'll bring my entire machine learning stack along with my model, and then I'll process my data. In both cases, those models are expensive and would like protection. And almost across the board, the data that will be fed into those models has confidentiality requirements. Particularly if you think about lots of those things are related to social media. So now we're talking about our pictures being mined in a cloud for the company that is running whatever the social network of choice is. But you find very similar requirements in edge devices. We were talking before about how so much data is being produced on the edge that you just can't afford to take all of that data and send it to the cloud. And so you're seeing more mining of that data being done locally, or at least closer to the edge. In that case, those models are equally valuable, if not more, because there's usually a significant commercial element to those. And what they would like to know is that somebody tampering with the edge device is not going to be able to extract those expensive models. And then the same thing is true of the top one. The data being processed here is typically very sensitive, either privacy or commercial, financial. And so this gives us an opportunity to say, well, if you protected the inference engine and whatever the application is, in this case over there, it's an image classifier, inside of an enclave, then that provides you with additional protection on both the model and the data. So what we did was we used the Graphene SGX from earlier in the conversation and put OpenVINO into an enclave. And now SGX is providing the isolation from the outside environment. The attestation, the network shield provides attestation so that before submitting the images into the classification engine, you get an attestation that says, this is OpenVINO. It's not something that's going to go spill out your images. it will run this particular model on it and respond back with the results. With some additional software changes, remember the goal here, since we were using graphene, there weren't any software changes to OpenVINO, but we could extend OpenVINO to also, rather than have the model start in the enclave, do an attestation out and say, I am an empty engine. I am protected by, I'm in XYZ cloud, and I am protected with SGX. It's safe to feed your model in, and then you do the attestation for the data. It's safe to feed your data in. And so we can now provide additional protections for both the sensitive models as well as the sensitive data that is being inferenced on the models using enclaves with minimal changes to the existing software. The changes would all be in the feeding end because the inference engine didn't have to change. So that was the first usage, or the first interesting usage. The next one is in our telco infrastructure. My animation isn't happening because it's PDF, so just pay attention to the left-hand side for the moment. So telco infrastructures used to be primarily fixed function devices, very expensive to develop, very difficult to upgrade if at all, and therefore very expensive to replace. But the upside is that they were super fast because they were very custom designed for that throughput. And many of them provided pretty cool security properties. Some of them were even tamper resistant, so that they could defeat certain types of insiders in the telco network. But all of that is super expensive. So we've seen a trend toward trying to replace those with software versions of them. Well, that's great because the hardware is much cheaper. Our hardware is fast enough now that it's still able to be fast enough compared to the ASICs to get the job done. It's much more flexible from the reuse perspective, and the upgrading is much simpler. Obviously, it's a software upgrade versus an ASIC upgrade or an ASIC repurchase. The downside is that the security promises are significantly lower because it's just software running in a VM. But as long as you're keeping it in your own data centers, you being the telco company, that math plays out, and it's still worth making that migration. But simultaneously, you've also got the trend of moving compute to places that are less protected than your own data center, and open environments like data centers owned by other people. And so these two trends don't mesh well. And so what our proposal is that enclaves can help you get back some of the security properties that you lost. Obviously, we're not going to be able to make it all the way to a tamper-resistant device, but can we get enough of the security properties back to make putting some of that telco infrastructure and software in a data center owned by somebody else work? And this is just a comment about the reusability. Most of these services are actually just a small number of primitives pieced together in different ways. Tuple lookups, filters, policy engines, some simple state machines. You can use these to build routers, packet handlers, VPNs, all this stuff. And so we've worked on a project called OMEC that implements all of those and is starting to build out open source implementations that we've partnered up with some telco providers on and released. If you Google this, you can find out who all those partners are, but I won't name their names here because I don't know if they want me to. If you look across the top of this, you've got basically your wireless access network on one side and the internet on the other side. And in the middle of that is the packet handling portion of the infrastructure. And we sort of zoom in on it as we come down. And this is one of the NFVs that I thought was worth illustrating how it would work and how fast it will work. And down here you've got your base station coming in, and then there's the service gateway, which basically what it does is it gets a packet, it cracks open the packet, figures out what customer the packet came from. If it's not from a customer, it throws it on the ground. If it's from a customer that hasn't paid for internet access, it throws it on the ground. If it is for a customer, then it sends some information off to the billing system. If it's a special customer, maybe it applies some special routing rules. If the destination is interesting, maybe it applies some special routing rules. And then it hands it off to the packet gateway, which converts the packet from wireless standards to Ethernet, and then passes it off to the internet. And so there's really no question about, can you put that logic in an enclave? There's nothing magical about that logic. Real question is, if you did put it in an enclave, would it have any chance of keeping up with a real telco workload? And the answer is yes. This is a picture of one of the prototypes that we built using those libraries that these components aren't open sourced yet, but they will be. And basically the key is avoiding entering and exiting the enclave. Once you're in the enclave and the memory that you're handling is hot in the cache, it is, and assuming it's a Xeon processor, it is Xeon speed. If it's a client, then it's client speed. The tricky part is when you jump in and out of the enclave, there's a whole bunch of cleansing that has to happen to make sure that things aren't inadvertently leaked out of the enclave. And so what you do is you just strategically pick what your cores are doing. You have one core that does miscellaneous stuff that we're not interested in. Then you've got one core that sets up outside of the enclave rings for input and output from the enclave. And then you put all the rest of the cores that you've got. In our case, it was an E3 Xeon server, because that's the biggest server that we currently ship that has SGX. And so it only had 4 cores, so you've got 2 of them in there. And those cores never leave the enclave. They stay in there just scooping data up into the ring and putting output into the ring. And they are able, even on our E3s, able to keep up with line rate or using a 10 gigabit card. We can get 90% of line rate with 20 gigabyte cards, which means if we had more cores, we would probably have no problem with that. We didn't have any bigger NICs yet. So we haven't really been able to fully push this. And you can imagine once we release SGX enabled, I don't know what our server group's correct term for the real servers, because the E3s are kind of like the tiny little single socket servers. Once we start releasing the multi-package, multi-socket servers, then you'll really see how far you can push this. But the exciting part was that it looks like, yes, we can keep up with these sorts of workloads. And enclaves will give us the confidentiality of the traffic that we want if the telco wants to move any of this to a data center that they don't own, as well as the integrity for tampering with that traffic that they would want. Blockchain. Yay. Okay, so I'm sure everybody knows about blockchain, and everybody knows about its usage as a means of building a cryptocurrency. But the reality is that it can be used for significantly more than cryptocurrency, but probably significantly less than many marketing people say it can be used for. There's a sweet spot in there. And for the purposes of our conversation, the many of those that are still real usages, not the made up marketing ones, but not cryptocurrency, the security bar is very different than it is for cryptocurrency, right? The amount that an attacker can afford to spend to break your system is based on the assets that system has. And when that system has large sums of money, it's a no-brainer to go and throw large resources to attack it. But if you start looking at some of the other usage models, supply chain tracking, where you're looking for a decentralized system and nobody wants to foot the bill for hosting the centralized system, data provenance systems where you go back to the health version where you've got lots of different providers of the data and you're looking for something decentralized, but you're not talking about something that is investing significant sums of money to break, then the question is, are there significantly cheaper ways of achieving the most expensive part of blockchain, which is the consensus algorithm? And we believe the answer is yes, obviously. We believe that the enclaves provide us with several opportunities to speed that up. But first, we sort of have to use an example of why the consensus portion is so expensive. Anybody who's familiar with Bitcoin and has a curious security mind will have read up on how the consensus algorithm works. You are basically trying to brute force a hash. The idea there is that based on the current block, everybody's looking for a nonce that when you hash that nonce in a block comes out to a hash with a certain pattern. And because we all believe that hash is computationally infeasible to break, the only way that you can do it is just by brute force, keep on trying different nonces until you find one. What this means is that there's no central coordination needed, which was the whole point. The beauty of the hash is that it's very easy to verify that someone found this magical nonce, because all they have to do is tell you the nonce, you calculate the hash, you see the pattern, boom, you're good. And assuming that nobody was able to break SHA, it's completely fair. Anybody could have found the magic nonce, with the exception of you invest more searching hardware, then you increase your chances, but that just sort of comes with the turf. You spent more, so you increased your odds. But unless you hit a certain threshold, then it still stays fair. But it's super expensive from a power perspective, and somebody's got to pay for that power. And those other usages that we were listing, it doesn't make sense for them to spend that on that power. And that whole category of, and marketing people say you could do this with it, but it doesn't really make sense. Most of those fall into it's because you can't justify the power costs. But, I just noticed no one else was there. If you step back away from the hash for a moment, you realize that the hash actually had very little to do with the end goal. Really what you were trying to do is create a random distribution of how the blocks are distributed, and to establish some notion of fairness of distributing who it is that is the leader next. And you need some way to prevent somebody from being able to forcibly be the leader multiple times over. And so that algorithm is referred to as proof of work, and there's been lots of research in desperately trying to find other options than it that are cheaper. And I purposely didn't go through the 7 or 8 different other alternatives that are in there. POET is another one. It's called proof of elapsed time. And basically all it is that all the endpoints pick a random number, and they wait that amount of time. And whoever waits the least is the one that had the lowest random number. And then they announce that I had the lowest number. And that works as long as everybody plays by the rules. How do you get everybody to play by the rules? Well, the answer is that you take that algorithm and you put it in an enclave that is now attestable. So now I don't just have to trust you when you say, my random number was a half a second. Instead, you announce an attestation saying, I was running this version of the POET consensus algorithm, and it picked a random number. This was my number. I waited, and now I'm announcing it. And assuming that you haven't broken something in the hardware, everybody knows that, yes, in fact, you did wait. They were random numbers, so it's equally distributed across the crowd. It's very easy to verify. You just have to look at the attestation and see, it says he has a small number, or it says he has the smallest announced number, and it's an attestation that says that it is the correct software and it did wait. And by doing this, you can imagine the power consumption of this is astronomically smaller. Even in the most conservative of estimates, say it took a whole watt to do that, pick a random number and wait. At 500,000 servers, you're talking about 5 gigawatts of power per year, compared to numbers last year for Bitcoin that were commenting that it consumes a small country worth of power at 50 terawatts. And so we think that while this is not the next way to protect your cryptocurrency if you're sold on cryptocurrencies, but rather this is a way to enable all the non-cryptocurrencies to build something inexpensively that has all of those distributed properties that and non-centralized properties that we liked. That is all I had. Really just trying to spur up some interesting thinking about how to use trusted execution environments in ways to do things that we otherwise couldn't do outside of some of the, I get bored about talking about building VTPMs and DRM and those sorts of topics. So this was interesting. I don't know that I trust your question.
OSs against the control channel attacks that plagued Haven?
I am not.
Has there been any progress hardening the library OS implementations against the controlled channel attacks that plagued Haven when it came out?
I do not know. I do know who would know.
Can I try to take that?
Sure.
My name's Andrew Bellman. I was the main author on Haven. The fundamental problem with the control channel attack is an architectural problem with SGX, pointing back to this man over here, that the OS can inject a page fault and observe the page that the enclave was trying to access at any time. And so it fundamentally requires an ISA change to fix. There has been a bunch of work on defeating those things using software mitigations. Mostly they're using things like compiler techniques to try to put all the memory accesses inside a transactional memory access so that you don't get the page fault in the first place, and you turn the page fault into a transaction abort. So there's various kind of fairly expensive hacks that people do by rewriting software to avoid them, but fundamentally they're an ISA problem with SGX.
Yeah, I was just sort of curious about the POET proposal there for blockchain. Like, how might such a thing protect against or complement protections against physical attacks? I mean, if you're talking about like literally making infinite money, it feels like your adversary would be willing to invest whatever reasonable thing it took to get to that infinite money spring. So I'm just curious.
That was why I started by saying that this is probably not appropriate for cryptocurrencies, because that's where you get infinite money.
Right.
If your goal is you're trying to do supply chain tracking of goods, then breaking that doesn't have the same unlimited return on investment, right? If you're trying to track fish through catching to the sushi bar, that's what I mean by supply channel stuff.
Thanks.
So yeah, I deliberately started with cryptocurrencies or usages that had no choice but to create their own new coin so that there was a currency involved in order to pay for it. Those usages are the ones that are not interesting for POET.
So what are the performance implications of running an SGX? I mean, I know the goal is to run unmodified applications in the enclave context, but in addition, the partnering of libOS, I get why you're doing that. The explanation makes sense, but the performance implications of that, if I look at kind of the ones you focused on, anything with secrets, I can sort of understand. The ML case, sure, it's an arbitrary workload. ML's hot and sexy, so ML, and maybe there's some proprietary thing that people want to protect against that, but you can say that for any proprietary workload that anybody has, right? Uh-huh. And the case on the 5G piece seemed to be more of stream processing. So like, what is the impact on execution with respect to memory and other things? Like if I have memory intensive workloads, what penalty do I pay to run inside the SGX context?
So there are two major factors that play into the performance of SGX. There's SGX memory. So when your enclave memory is hot in the cache, you can get to it as fast as any memory that is hot in the cache. If it is not hot in the cache, then there is a performance hit because that memory does get encrypted and decrypted on the way out to memory, because we try and mitigate memories or attacks on memory. And this is where the streaming worked out so well, because there's not as much cold memory involved in the transaction. So if you can keep all your memory warm in the EP or in cache, then you're talking about being as fast as normal processes from memory access.
But up to what limit? Like, how large is that? Is it all of memory?
Well, no, that was talking about just the cache,
Right.
which is L2 cache
Oh, so,
or LLC.
okay, so for cache, but what's the total amount of memory available to me in the?
So the next piece of the puzzle would be, and there is a hit. We've published some papers on it for what the performance hit for going and fetching encrypted memory is. I don't know what it is offhand, and that applies as long as you can also fit all of your enclave memory in the EPC, the enclave page cache, which is a limited resource. In clients, it was fairly small at 128 megs. When and people have tried to put server workloads in it, and we did with the NFV stuff. But if you go beyond that, then you start thrashing on paging in and out of it, and that you will suffer significantly from. When you start getting to our big real server class servers, you will have significantly more EPC space available, though I can't comment on when those will come out or how big that is, but it will be significantly bigger when you're on a real cloud class server, like our multi-package servers. And then the third factor is the entries and exits that I mentioned before. So if you can structure your software, and this is where, if you're using a libOS style model, this won't help you as much because you will not have optimized your software for not leaving. And then that would be very workload dependent on how often you take the exit. I know that didn't give much of an answer there, but those are the factors that would play a role, and I don't really have numbers on them that I can quote.
Hey, so the whole subject here is enabling cool uses of SGX. Something that would enable a lot more cool uses of SGX would be the availability of the protected audiovisual path to the general public, so that you could do I/O from a SGX enclave to a human without trusting the rest of that stuff in between.
Uh-huh.
Is that something that we might be able to leverage as the public at some point in the existing future?
I, as being someone from Intel Labs, am not able to comment on what things we will or won't productize in the future.
Fair.
Unfortunately, I cannot answer your question, but I agree with it. It would be cool if we could do better trusted I/O from inside of the enclave. We have been working on in the labs on ways. It won't reach out to the user the way you've described, but we have been looking at, for FPGAs and GPUs and accelerators, without having to add a bunch of special hardware that would take time and gets us into the when does it get productized. How can we create encrypted channels to those devices so that we can get that type of I/O, but without putting encryption in your camera, it's tough to create that end-to-end pipe. So there's a bunch to do there that the labs can't do alone.
So going back to your telco example, one of the powers of SGX is that you open source the enclave, anyone can audit that code and then therefore trust it as long as it has the right signature. In the telco example, how does that kind of open transparency jive with like lawful access and pen register requirements that the telcos have on them?
So your question took like a left turn in the middle of it. I was going to say that where I thought you were going was, how do you use attestation and knowledge of the open source? And I was going to say that the attestation only has to be meaningful to the entity that is receiving the attestation. And the attestation is not going to one of our cell phones. The attestation is going from the platform that is being leased in somebody else's data center to the telco provider that wrote the software, So he knows what the software is. To him, it's open source, but it doesn't mean it's necessarily accessible to everybody else. It's him that is going to judge it and say, yes, I should forward, or technically, I should give the keys that are needed to decrypt the data that's coming from our towers to that enclave over there.
That makes sense, but it's a bummer.
Yeah. Now, there may be other driving factors that drive them in some environments to release that wider. But the attestation, it only needs to be opened to whoever's seeing the attestation. And in that particular usage, it would be the telco company probably.
Are there any plans from Intel to not necessarily open source, but somehow allow me to run my own attestation services instead of using the Intel server to attest the VM? I understand the enclave. I understand that.
Are you familiar with the decap tools?
Yeah, but do they replace really all the mechanisms the Intel servers provide? Let's say I want to run this overall system on a data center that's not accessible from the internet.
So the decap, data center attestation primitives, is something that we've released for this specific purpose. The attestation infrastructure, the EPID attestation infrastructure, that was designed for clients. And that was basically a bunch of us on the SGX team were previously in TCG. And TCG spec'd out this whole infrastructure and said, if you build it, they will come. And nobody ever built the infrastructure. And so we said, if SGX attestation is going to be successful, we have to actually build that, not rely on someone else. So we built one targeting clients, which was the EPID one. But that was never really expected to support clouds, right? And so at a similar time frame to when we released the E3, our low-end servers with SGX, we released decap, which when paired up with flexible launch control, which is on our E3 line, you can write your own quoting enclave, you can write your own backend. We have services that offer the certificates that you would need for your attestation server to be able to verify one of those attestations. The certificates, because of manufacturing issues, we can't ship them in the platform, but we host services where you can come and collect them. And then we have an ECDSA quoting enclave and library for verifying those quotes that you can use with that, or you can feel free to write your own. And that's all available now off of our webpage.
Okay, thank you.
So, cool question on your consensus algorithms use case. Does SGX allow you to actually call sleep without the relying on the normal world operating system?
I'm not entirely sure how we spin for that amount of time. I would have to look into that because you're right. Normally, you would that would be a system call. I'm not sure exactly how they've implemented that.
So that was built somewhere as a proof of concept?
Yes,
or not? Okay.
and we've open sourced it, and it's out there. If you Google Poet, you can download it and see how it was done. The person that wrote it is across the cube aisle from me, so I usually just ask him those questions.
Thank you.
But as he is not here to ask, I can find out the answer to you, or answer for you before tomorrow, though, if you're very interested. Okay, thank you.